Okay, I'd like to walk you through homework problem 5.1, a little bit what I did in class, but finish through the entire problem. But I want to do it without the numbers. You have the numbers here on the example problem, so I'm just going to work through the equations and the thinking process, try and help you walk through what it is you really need to know and understand for a cold air standard Otto cycle. All right, so let's get started. Okay, I have a couple things given for this problem. I have the initial temperature and pressure given. I have R, the compression ratio, given, and RP, the pressure ratio, given. So let's just say a few things about those two ratios. The compression ratio, R, is V1 over V2. That is the largest volume divided by the smallest volume in the cycle. It also happens to be the volume ratio for the first process. And then the pressure ratio, we're going to put a subscript P on that, and that's the pressure rise for the second process, which is P3 divided by P2. And with these two parameters, we define the entire cycle. So that's all that we need to work through the entire problem. R is generally a number around 10, and RP maybe somewhere around 2. So to give you some idea, they're both going to be numbers that are greater than 1. And if we do a little PV diagram, it's a V. We start here at a large volume. It compresses isentropically to state 2. I'll put a little S on here, that's constant entropy line. Then we compress at constant volume to state 3, so that's a vertical line. And then isentropic expansion, another isentropic line here, to state 4. And then finally constant volume heat rejection from 4 to 1. So 2 isentropic processes, 2 constant volume processes. And let's review the 4 processes for our engine. We have compress it, and heat it, expand it, and cool it. And this is process 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So how do we compress it? Well, we compress it isentropically, or delta S equals 0. How do we heat it? Some property remains constant there at constant volume, so delta V equals 0. How do we expand it? Again, isentropically, so some process that's constant, delta S, or entropy is constant, delta S is 0. And then again, specific volume is constant, so delta V equals 0. And for most of our engine cycles that we're going to look at, we always have one property that's constant, or delta S is 0 for each process in our cycle. So delta S equals 0, delta V equals 0, delta S equals 0, delta V equals 0, or constant S for the compression, constant V for the heating, constant S for the expansion, constant V for the heat rejection, cooling. Okay, so that gives us a framework, and if we understand this, when we look at a cycle, if we changed one of these, if our first process was a compression process, but instead of delta S being 0, maybe delta T was 0, well then that would give us another cycle that doesn't have a name at this point. So, but we can certainly create our own different processes to produce power. This happens to be a common one, the Otto cycle, similar to a gasoline engine, or models gasoline engine fairly well. All right, let's start then looking at But we want to ultimately find efficiency, but to do that we're going to need to know all the temperatures throughout the cycle. So we already know T1 and P1, so let's go after T2 and P2. And there are a number of ways to do that. This is for everywhere, right up here at the top. We're working with air as an ideal gas. For the cold air standard, we're using constant specific heats. And more specifically at T equals 300 Kelvin. So K in this case would be the specific heat ratio is always 1.4. And then for some processes we have that the entropy doesn't change. So for this first process, so delta S from 1 to 2 is 0. So this is an isentropic process. So it's an ideal gas, constant specific heats, and an isentropic process. And for those three conditions, we know that PV to the K equals constant. And we can write that as P1 V1 to the K equals P2 V2 to the K. And so what are the conditions for this? Ideal gas, CP, CV are constant. Usually when we say we have an equation with K in it and it's not a function of temperature, then we're talking about constant specific heats, or anytime you see an equation with a K in it, that's to or minus constant specific heats. And then isentropic. So if these three things hold true, we can use this equation I just boxed in. So we'll write that as P1 V1 to the K equals P2 V2 to the K, because process 1, 2 is an isentropic process. So we can't use this, say, for between states 2 and 3, because that's not an isentropic process. And then I can rewrite this as P2 equals P1 times V1 over V2 to the power K, or if I recognize V1 over V2 as R, P1 R to the K. And then if I use the ideal gas relationship, which is which I can use for any process, and I write it as P2 V2 equals RT2, and divide it by P1 V1 on the left side and RT1 on the right side, since those two terms are equivalent, then I get that the R's cancel and become 1, and V2 over V1 is, I can replace as 1 over R, and now I can write multiply both sides by T1, and I get that P2 over P1 times T1 over R equals T2, and with a little bit of arranging, it's fairly easy to show that T2 then equals so P2 over P1, this term right here I just found is R to the K, and then divided by R, so R to the K divided by to the power K divided by R times T1 is equal to T2, and then we might note that R to the K divided by R is the same as T2 equals T1 R to the K minus 1. Now you can memorize all these steps, but to me I would rather just remember PV to the K equals a constant for constant specific heat, it's isentropic process, and this idea of writing out the ideal gas law and then dividing it by the other end state using the ideal gas law and then rearranging that to find the other relationship, either temperature or pressure, is actually the easy way. And the advantage of doing this is if the first process is something different, it's not an isentropic process, then I just use the appropriate equations, derive what I need. But I will always use the relationship like Px Vx equals Rtx, and then divide by Py Vy Rty for every single step of either the air standard or the cold air standard. So that's a good way to proceed. All right, I'm going to continue on, take a snapshot of this, and move on to state 3. So we're finished with state 2. Let's erase this. Now, of course, if I know what R is and I know what T1 and P1 is, I can just plug in those values. I know K is 1.4. It's always going to be 1.4 for air. The problem is cold air standard. So let's move on now to process 2-3. So from 2-3, the volume, change in volume from 2 to 3 equals 0. So it's a constant volume process. Now I'm going to write this ideal gas equation again. P3 V3 equals RT3 divided by P2 V2 RT2. And even if I think I don't need it, I'm going to write this down because I know I'll always use it. The R's cancel, so that becomes 1. And then it's a constant volume process, so V3 over V2, if V isn't changing, that equals 1. So those terms cancel. And I just am left with the ratio of the pressures equals the ratio of the temperatures. Well, that's convenient because we've defined RP as P3 over P2. So if I'm given RP and I just found P2, then this is as simple as P3 equals RP times P2. And T3 is equal to RP times T2. So state 1 was a little more challenging. State 2 was very, very easy. Now finding state 4 is the same as finding state 2 from 1, and then we just have the last process to connect back. So it's really easy to find these 3 states, state 2, 3, and 4 from 1, and then finally we'll relate them. So let's move on to state 4. And again, I strongly recommend don't memorize the final step. Work through the process and try and do it on your own. Solve the whole problem symbolically, where you don't memorize anything, and all you start with is either PV to the K equals a constant, or PV equals RT, and then make a ratio of those. All right, so let's take the next step. So we've got the next step is delta S from 3 to 4 equals 0. So this is an isentropic process. So again, I can use PV to the K equals a constant. And I'm going to use states 3 and 4. And the other equation I'm going to use is P4 V4 equals RT4 over P3 V3 RT3. And I'll just divide one equation by the other. The R's cancel. And in this case, the V's don't cancel, so I'm going to have to find some kind of relationship there. But if you'll notice that V1 over V2 is what we call the compression ratio. And V4 is the same thing as V1, same specific volume. So I can replace V1 with V4. It's the same V1 is right here on the graph, and V4 is at the exact same place. That's why it's a vertical line. They're both at the same point. And V2 and 3 are both at the same point. V2 is here, and V3 is also at the same point. So V2 is the same as V3. So this thing right here, this ratio, I can replace with R, the compression ratio. Now that's true just because I look at the diagram and can make that connection. If maybe one of these processes is in constant volume, well then I don't do that. So it's just simply a matter of observing, what process is happening here and simplifying the equations appropriately. Now let's look at the other equation. So I've got, I'm after P4, so let's write P4 equals P3, and I'll have V3 in the numerator, V4 in the denominator, to the power K. Now V4 over V3 is R, so this is 1 over that, so this is 1 over R. And so I get that P4 equals P3, and I can either do divided by R to the K or times 1 over R to the K, but I'll do divided by R to the K. And then I can use this in the other expression, so P4 over P3 equals 1 over R to the K, and I get that then T4 equals T3, and I'm using this expression up here, and I've got times P4 over P3 and then times R. And P4 over P3 from this expression is 1 over R to the K, so this is 1 over R to the K. And I can write R as 1 over R to the minus 1. And then I can add those powers together, and I get that these two terms become 1 over R to the K minus 1. And so finally from that I get that T4 equals T3 divided by R to the K minus 1. So now I have an equation for state 2, temperature and pressure, state 3, temperature and pressure, and state 4, temperature and pressure. And now all you need to do is find the work for each process, the heat transfer for each process, and then finally the efficiency. So we'll save this again and move on. Sure I erased all that. Okay. Alright, so let's start with process 1, 2 again. So from 1 to 2 now, we know that Q1 to 2 minus W1 to 2 equals delta E 1 to 2. And we have, that's the same as delta U 1 to 2 plus change in kinetic energy 1 to 2 plus change in potential energy 1 to 2, but we're recognizing that there's no change in potential energy, there's no change in kinetic energy, so all we're left with is the internal energy. Remember, it's a piston cylinder assembly, so especially if it was laying on its side, then there's no change in elevation, but even vertically mounted, there's not a significant change in elevation. The system's not accelerating, so those are good assumptions. And then for an ideal gas, we can write that delta U equals M times the constant volume specific heat times the delta T. So mCV delta T. And then for process 1, 2, we know, well, that was a isentropic process, so it's reversible and adiabatic, so Q is 0, so we get that the work equals mCV delta T. And in this case, if we want the work in, then the work in would be m times CV times T2 minus T1. Here I really have negative W is equal to delta U, so we end up with then that if we call negative work in, then we get mCV T final minus T initial, which is the same as our first equation, except I'm using work out is positive according to the first law, so when I write work in, it's negative W. All right, then for the next process, we have Q23 plus W23 equals mCV. Let's put T3 minus T2. And I know for this process, since the volume isn't changing, there is no work for that process. Work equals integral PdV, and there's no dV. So I get that Q23 equals, which is the same as Qn, is equal to mCV T3 minus T2. The next process, negative W equals mCV, well, let me write it as Q minus W again. We'll cross out the appropriate terms. So Q 3 to 4 minus W 3 to 4 equals mCV T4 minus T3. And again, it's reversible and it's adiabatic, so no heat transfer for 3 to 4. And here I have negative W34. It would probably be better to write this as work out from 3 to 4 is equal to mCV T3 minus T4, where I multiplied the entire equation by minus 1 just to end up with a positive value there for the work out. So now I have all my equations for the work, the Q in, and now I can write the efficiency. I'm going to erase the top part of this. Let's have some room here while I can look at those equations still. So ultimately, the efficiency equals the net work over Qn, which would be W in, or let's do W out, minus W in over Q in. And that's going to be, my work out is T3 minus T4. Minus my work in, T2 minus T1. Divided by Qn, which is T3 minus T2. You might say, but I thought every one of those terms was multiplied by mCV. It is, but mCV times each term, I can divide the numerator and denominator by m, get rid of the m, divide by CV, and those drop out. And that's because the specific heat, remember, is a constant. If it wasn't, then the specific heat would vary with temperature. I couldn't do that. And so I'm just left with a simple expression as a function of temperatures. I know all the temperatures, and now I can plug in values. I'm going to erase and do one more equation, which is, can I put in the functions for temperatures and somehow come up with an equation symbolically for efficiency? And in fact, we can. Let me take a shot of this before I erase. And then let's let's do this final step. So I have everything there is in terms of temperature. So the efficiency is a function of T1, T2, T3, and T4. And since T1 or T2 is a function of T1, T3 is a function of T2, and T4 is a function of T3, I should be able to write this whole thing with just T1 in there. So I'm going to write this thing out. Okay, let's write out the equation for efficiency, which is a function of all the temperatures, but in this case we're going to replace each term with the equation that we have for temperature. So we've got that T3 is T1 times Rp to the k minus 1 times Rp. T1 times Rp to the k minus 1 is T2, and T2 times Rp is T3, and then minus T4 is the same as the first term, but then divided by R to the k minus 1. Not Rp to the k minus 1.
We have to discuss something quickly, 5 minutes. We don't have time.
Okay.
He doesn't have time, I don't have time.
Okay, let's see if we can come up with a simplified equation for efficiency, putting in all the terms that we have for temperature. So we have that T4 equals T3 divided by R to the k minus 1. But then we can write T3 as Rp times T2 over R to the k minus 1. And then we finally have that T2 can be written as T1 times R to the k minus 1. So that's T2 times Rp divided by R to the k minus 1. And we see that the R to the k minus 1 cancels out of this, and we get that T4 over T1 equals Rp. So if we start to replace some of these terms, T3, which is Rp times T2, which is, let's write that one out too. So T3 is Rp-T2, and then which is Rp-T1 over R to the k minus 1. Actually, T1 R to the k minus 1. Alright, let's just start with each one. Alright, let's come up with a simplified expression for efficiency with all these temperatures. And let's write just a quick summary again of the T2 equals T1 R to the k minus 1. T3 equals RP times T2, so that's T1 r to the k minus 1, that's T2 times RP, and T4 equals T3 divided by r to the k minus 1. When we look at T3 and divide it by r to the k minus 1, we'll drop the r to the k minus 1 and we get T1 RP, because we had r to the k minus 1 in the numerator and r to the k minus 1 in the denominator. So now when we write out our equation for efficiency, we've got T3, which is T1 r to the k minus 1 RP minus T1 RP, which is our T4, minus T2, which is T1 r to the k minus 1 minus T1. And all that's going to be divided by T3. Minus T2. So now everything's in terms of T1 and RP and r to the k minus 1. Now we see that every single term has T1 in it, so we can divide the numerator and the denominator by T1, and this becomes a 1. So the efficiency we see is actually not a function of T1. Then we can do a little manipulation here for the denominator. We see that both terms have an r to the k minus 1 term. So we have RP minus 1. And then in the numerator, we've got a few terms. Let's write out r to the k minus 1 minus 1 times RP, and minus r to the k minus 1 minus 1. Now let's rearrange a few terms in the numerator. So I have, leave the first term there, r to the k minus 1 RP. Let's bring the third term next, r minus r to the k minus 1. Group those two together. And then we have minus RP, and then minus 1, so plus 1. And group those two together. Actually, yeah. So minus minus RP, and then we have plus 1. If we want to group it together, it'd be RP minus 1. I'll give it one more try. All right, so let's rewrite the numerator as the first term minus the third term, and then minus RP and plus 1. And if we group these two together, then we can factor out a -1. And then the denominator we can write as rp to the k minus, or r to the k minus 1. rp minus r to the k minus 1. And we notice that the first term in the numerator is the same as the denominator, so we can write that as 1 minus, we have rp minus 1 over, and if we factor out r to the k minus 1, we're left with rp minus 1. And then we note that rp minus 1 cancels, and we get 1 minus 1 over r to the k minus 1 as the efficiency. And here we just put in the values for, or the equations for temperatures, all as a function of T1, and things simplify quite nicely. So that's another way to come up with efficiency, although we'll get the same result if we calculate all our temperatures and put that in. But if we don't need the temperatures, then a Otto cycle with K of 1.4 and compression ratio of 10 will just simply be 1 minus 1 over 10 to the 0.4. And we don't need to know all the details of the work and the heat transfer and all the temperatures. Of course, if we want all that information, then we can calculate it as we did in this problem.